Now I'd just like to do a quick recap on what we did here in this lecture on node voltages. We began with a circuit analysis toolbox, and we used two of these analysis techniques to derive the node voltage method. We considered the difference between node voltage and voltage difference. The voltage difference was the hike up the hill, and the node voltage was the vantage point that we arrived at. We considered this method that we've used to calculate node voltages before, and then we're going to use the VA minus VB equals IR form in future work. Here are the two types of branches that we might have, one with a single resistor and one with multiple resistors. And then we considered the KCL, or the sum of incoming currents equaling the sum of outgoing currents. And we did a simple example. The one tricky thing here was that we defined all of our currents as being outgoing, and don't allow any of them as coming in. We considered 5 different types of branches: a single resistor, a dual resistor, a simple voltage source, a voltage source with a resistor, and a simple current source. We looked at the steps of performing node analysis, where we first define our nodes, we select one as the reference node, we assign variable names to all, and then we write the node voltage equations and solve those using matrix equations. We did the simple problem here, where we moved the resistor from this side up to the top so that we could make this a simple node voltage equation, and we ended up with two equations two node equations plus a definition for our ground and the voltage source coming in here. Then we did a more complicated example where we included a dependent current source, a dependent voltage source, and the challenge of the dependent voltage source is that it was right here in between these two voltages, so it had to be considered as a supernode. I showed you two ways of considering the supernode. One was to block off the whole part of the circuit and consider all of the outgoing currents to be zero. The other was to define the current going through a voltage source. Both of those are key elements of electrical analysis. The idea that you can block off any part of a circuit, including this node, you could block off any part of the circuit, and all of the ingoing currents would have to equal all of the outgoing currents through any base part of your circuit. The second basic idea here is that you can have a voltage source, and the voltage source does always have a current going through it, unless of course the current ends up being zero. So those are two basic ideas that we use to our advantage in this circuit. So what we have now is a circuit analysis toolbox. Before we had node voltage, we would use Kirchhoff's law, start with our sources and resistance, find the currents, the branch currents. Then we would take the branch currents and one node in order to find the node voltages, or the voltages at any other node. Now we have the node voltage method, and what we do is we bring in our sources and our resistance, and we solve directly for the nodal voltages. This method is very popular for several reasons. One is it's quite straightforward and simple. The other is that it's very easy for us to measure node voltages as opposed to measuring currents, which is not quite as easy. So that's our basic method, and I hope that you find it very useful in your circuit analysis.